All right, if you're a formulation engineer working in the coatings industry, you already know the deal with HDI, hexamethylene diisocyanate. It is absolutely the gold standard when we're talking about high-end top coats. I mean, its weather resistance is basically legendary at this point. But it comes with a massive everyday headache for us, right? It dries incredibly slowly. So if HDI is such a premium material, why are we still fighting with these frustrating dry times? Well, fixing this doesn't mean we have to sacrifice that gorgeous, non-yellowing finish. In today's explainer, we're going to completely break down how to accelerate HDI curing so you can create high-performance, truly elegant solutions for your next formulation. Let's dive in.
So let's face reality here and look at the classic innovator's trade-off we deal with every single day. Over on the left, we've got our aliphatic HDI systems. These give us that beautiful 5-star weather resistance, holding on to their gloss year after year with 0 yellowing. But the drying speed? Yeah, a generous 2 stars on a good day. Now flip over to the right, aromatic TDI systems give you that blistering 5-star drying speed for your high-volume lines. But the second you put it out in the sun, weather resistance completely tanks to a dismal 1 star. It's going to yellow almost instantly. Usually you want weatherability, you just accept the slow dry. You want fast drying, you accept the yellowing. But what if we actually engineer a way to grab the best of both worlds?
To pull that off, we need a really solid systems engineering approach. Here is our roadmap for this explainer. First, we'll dig into the molecular root cause of this slow curing. Number 2, we'll look at the eco-friendly catalyst upgrade. 3, we'll talk about tweaking your core formulation parameters. 4, we'll cover some smart blending strategies. And finally, we'll wrap it all up with a master formulator's mindset.
Okay, let's jump right into section 1, the molecular root cause. Exactly why does HDI dry so slowly?
I love this analogy because it hits the nail right on the head. HDI is basically like a stubborn lock that needs a really strong key. Think about it at the molecular level. HDI is an aliphatic isocyanate, right? Its structure is just a saturated carbon chain with these isolated NCO or isocyanate groups just kind of hanging off the ends. There are 0 double bonds, no aromatic rings to kickstart reactivity, and because it totally lacks that aromatic ring structure, the electrophilicity of that carbon atom is surprisingly weak. That makes it so much harder for the hydroxyl groups in your polyol to actually attack it. So look, if your HDI coating is taking forever to dry, it's not necessarily a bad formulation, it's just fundamental molecular chemistry working against you. Moving right along to section 2. Let's talk about the eco-friendly catalyst upgrade and why we absolutely have to move beyond traditional tin. So, if HDI is that stubborn lock we just talked about, we obviously need a catalyst to act as our strong key. Now, for decades, the industry's go-to was organic tin, specifically DBTDL. It got the job done, sure, but the harsh reality of relying on legacy tin is really starting to catch up with us. First off, it has terrible selectivity. It accelerates the main reaction, but it equally accelerates side reactions with moisture, which massively spikes your bubbling risks. Second, it gives you an incredibly short pot life. That just creates a super stressful, narrow application window for the end user. And third, and maybe most importantly right now, the toxicity. With global regulations like REACH coming down hard on organic tin, finding a green alternative isn't just a nice-to-have anymore. It's strictly mandatory. And this is exactly where beta-diketonoate zirconium steps in and completely changes the game. Look at this comparison. Zirconium matches that high catalytic efficiency of tin, so you're still significantly shortening your drying and gel times. But check out the pot life column. Zirconium delivers a 5-star, genuinely long pot life. The initial viscosity curve stays nice and gentle, giving you a huge application window. But then, as the solvents start to evaporate, boom, that curing speed ramps up beautifully. Plus, zirconium is highly selective. It heavily targets the isocyanate hydrocell reaction, which means your bubble control goes through the roof. And the best part, it's green chemistry. It aligns perfectly with strict eco-compliance and corporate sustainability goals. All right, section 3, tweaking core formulation parameters. Let's get into the internal mechanics of the system. Upgrading your catalyst gives you fantastic external help for sure, but we can't stop there. We have to tune our internal dials too. The first major lever you can pull is your NCO to OH molar ratio. Now, theoretically, a perfect 1-to-1 match sounds great on paper, but the actual sweet spot to accelerate real-world curing is bumping this ratio up to somewhere between 1.1 and 1.5. A higher NCO concentration literally pushes that main reaction to happen faster. But more importantly, dialing in that excess NCO unlocks a powerful secondary mechanism, moisture curing. Let's quickly walk through exactly how this moisture curing kicks in. Step 1. That excess NCO we just talked about reacts with ambient moisture in the air. Step 2. This reaction creates a highly unstable carbamic acid intermediate. Step 3. That intermediate rapidly breaks down, and when it does, it releases a molecule of carbon dioxide. Finally, Step 4, what you have left is a highly active primary amine, which immediately grabs onto another isocyanate group to form a rigid urea linkage. This secondary network makes your coating denser and harder incredibly fast. But you've got to be careful here. Look at Step 3 again. CO2 is released. If you push your NCO ratio way too high, or if your coating films over too quickly, that CO2 is going to get trapped, and you'll be left with a completely ruined surface full of pinholes and bubbles. It is a very delicate balancing act.
To manage that balance and keep the speed up, we have to engineer the polyol side of the equation. Here are your rapid dry design rules. First, you want a resin with a high glass transition temperature, or TG. That helps you hit physical surface dry much faster as those solvents flash off. Second, you really need a narrow molecular weight distribution. You want to avoid those low molecular weight components that act like sneaky plasticizers and soften your film. Third, aim for a moderate acid value. Keeping a few carboxylic groups in there actually provides a neat little autocatalytic effect. And lastly, prioritize rigid main chains, think cyclic structures, over flexible aliphatic chains, so you can build that early mechanical strength right out of the gate.
Moving to Section 4, Smart Blending Strategies. Let's talk about the power of synergy.
Sometimes, even with flawless internal parameters, pure HDI still needs a little external muscle. We generally see two main blending pathways here. On the left, blending HDI with IPDI. This is an internal optimization. IPDI has this rigid, six-membered cycloaliphatic ring that significantly boosts your early hardness and drying speed, but crucially, it completely retains that 5-star weather resistance. This is your sophisticated, high-end choice for premium top coats. On the right, though, we have an aggressive external enhancement, blending HDI with aromatics like TDI. This gives you an absolute massive speed boost, perfect for blazing fast assembly lines. But, as you'd expect, you entirely sacrifice your weatherability.
And that brings us to a hard, non-negotiable rule. The red line. If you are using an aromatic blend to chase drying speed, you can absolutely never use it for white coats, light colors, or high-gloss clear coats. Because of those aromatic rings, UV yellowing isn't just a possibility, it is an absolute guarantee. Aromatic blends should strictly be reserved for primers, mid-coats, or really dark top coats where a bit of color shift isn't going to ruin the final product. Ignoring this rule will 100% lead to catastrophic and incredibly expensive product failures out in the field. Don't learn that the hard way.
Finally, Section 5, the Master Formulator's Mindset, and why systems thinking is absolutely everything.
Elite chemistry is never just dumping a bunch of ingredients into a vat and hoping for the best. It requires what we call three-dimensional synergy. You upgrade to zirconium catalyst to get that green, highly selective efficiency. But as you do that, you have to actively calibrate your NCO to OH ratio and your polyol TG right alongside it. Need a little extra push? You blend in some IPDI. The key takeaway here is that these variables are entirely interdependent. If you crank up your NCO ratio, you better adjust your zirconium dosage to manage the CO2 outgassing. If you swap to a high TG polyol, you've got to keep a really close eye on your pot life. Pulling one lever always shifts another.
It's a really delicate, beautiful balancing act when you get it right. So I'll leave you with this to think about next time you're looking at your current formulation process. Are you just stacking materials, hoping to force a faster dry time, or are you truly engineering a system? Mastering how all these variables interact is exactly what separates a good formulator from a truly great one. Thank you so much for joining me for this explainer, and I'll see you next time as we continue to decode the incredible chemistry behind high-performance coatings.